Today's lesson is again about counting the number of possibilities, but this time we're going to use permutations and combinations. A permutation is the arrangement of distinct objects without repetition into an ordered situation. So the order matters. You'll hear a lot for permutation. So if you're arranging 6 ladies on a bench, that would be a good example of a permutation because, first of all, we're talking about arranging. That's a key word in permutations. And we aren't going to repeat those ladies on the bench, and they are distinct ladies. And we're talking about a certain order, which is what arrangement means. For a license plate, we are definitely concerned about the order of the letters on a license plate. Although we can have repetition of letters, so you won't be able to use a permutation on a license plate. 8 teams for first through third place. Well, they will be distinct teams. We won't have repetition of teams. A team can't have first and second place. And I would say the order matters. It matters whether you have first or second or third. Like, those are important distinctions. So I would say yes, that would be a good example of a permutation where the order that you place definitely matters. Choosing a boy and a girl from a class. I'm not sure that would be talking about an arrangement. I think we're just selecting a boy and a girl. It's not necessarily an ordered situation, so that doesn't sound like a permutation to me. Free lunch for 10 lucky students. I don't think we would repeat any students, but I also don't think you would care which order you would call those 10 lucky students in, so I don't think that would be a permutation because the order wouldn't necessarily matter. Flipping a coin 8 times, there would definitely be repeats, right? So since there's repetition, a permutation couldn't be used for flipping a coin. There's a formula for using permutations. Again, permutations, the number of ways to arrange in order n distinct objects into r positions. You'll often see that denoted npr, or sometimes p sub n comma r. The calculation goes n factorial over n minus r factorial. That seems complicated, so let's do an example. If there were 8 teams playing for first, second, and third place, the n distinct objects would be the 8 teams that are playing for those places, and the r positions would be those 3 places that they're playing for. So if we were wondering how many different ways those 8 teams could place first, second, and third, we could do 8p3. And to calculate that, we would just take 8 factorial divided by 8 minus 3 factorial, or 8 factorial divided by 5 factorial. Have you ever seen this little factorial hack where if you write out the factorial, you can cancel a bunch of the numbers? So this winds up just being 8 times 7 times 6. So 8p3 comes out to be 336. And so there are 336 different ways that those 8 teams could wind up placing first, second, and third place. Now there is a way to do permutations on your calculator. Here's what you do. You would push the 8, and then you go to Math. If you arrow over to Probability, you'll see that there's an NPR as your second choice. 8 NPR3 is the way that we could enter that, and that will just pop up that 336 ways to arrange 3 objects, choosing from 8 total. Now for permutations, we could also do that the old-fashioned way, where we make those little boxes and we just think, okay, how many choices do I have for the first box? There are 8 choices for the first place team. Once we place one of the teams there, we have 7 choices for the second place team. Then we only have 6 teams left to score third place, and that comes out to 336, and you'll notice that that matches how that 8p3 turned out. So all of these are different ways of calculating a permutation. a set of triplets get drawn from the student body in birth order to pie Mr. Speece's face, what are the chances? So first of all, how many different sets of 3 students from the student body are even possible? That would be our bottom number on our probability. Well, if we have 350 students in the school, and we're caring about order in this case, how many different ways are there to choose 3 students? That's going to be our bottom number. Over 42 million sets of 3 if we care about order. And currently I can think of 2 sets of triplets, and if we care about the order, there would only be 2 groups out of those 42 million groups that would include our sets of triplets in birth order. So I would say that our probability would only be 2 out of over 42 million. So what are the chances? So low. 4 senior boys need to be arranged at a table for the variety show Da Deeks skit. How many arrangements are possible? So again, we're looking for those keywords. In this one, it was birth order. In this one, we're talking about arrangements. So that's our key that we're talking about permutations. First, we'd need to know how many senior boys there are. I'm just going to take a stab at this and estimate that there are 50 senior boys this year. And we are going to take permutations of 4. Over 5 million different ways. Why are these numbers so huge? Have you ever tried doing arrangements of things? Let's say that we were arranging the letters in the word home. How many different ways can you arrange those letters? That was 24 different ways. And that was only 4 letters. So you can imagine if you're choosing from 50 or if you're choosing from 350. That's why those numbers get so huge so fast. All right, now a combination is the number of groupings of distinct objects with, again, no repetition, where order is not important. So the main difference, order not important for combinations. So if we were doing a selection of 5 choir members to sing at Mass, would you say that the order we choose them is important or not so important? I would say a group of 5 choir members is just a grouping, and that to me says combination. We would be choosing different choir members, we would have no repetitions, so a combination would describe that well. A locker combination, the word is right there. However, doesn't the order matter on a locker combination? So the word combination is so misleading. More like locker permutation. But wait a minute, can you have repeats in a locker combination? So really it's not a permutation either if repeats are allowed. So I would almost say neither. Unless you don't allow repeats, then it could be called a locker permutation since the order is important. Choosing 4 problems from a worksheet to grade. Sometimes I do that for homework, so I'll choose 4 problems at random to grade on your worksheet. I'm not going to choose the same problem twice, so repetition isn't a thing. They're going to be distinct problems. Does it matter what order I grade them in? Not really. So I would say that's a combination. So if there were 20 problems and I were choosing 4 problems, that's how I would calculate the probability that I would choose a certain 4 problems at random. If I were appointing 3 people for president, vice president, and treasurer, those are certain positions, right? Distinct positions, and I'm going to nominate somebody different for each position, so no repetition. And when we're talking positions, we're talking a certain order, so that's a permutation. So some keywords that we're looking for: groupings are combinations, positions are permutations, arrangements are permutations. Just some key things to look for. And here's our special formula for combinations. NCR is n factorial over r factorial times n minus r factorial. So here's that one I was talking about earlier. If there are 20 problems on a worksheet and I'm going to choose 4 problems at random to grade, how many different ways are there for me to choose 4 problems? N is the number of distinct objects. There are 20 distinct problems on the worksheet, and I'm going to choose a group of size R, a group of 4. So I'm going to calculate 20 C4. And if we apply that same hack where we would cross off 16 on down with the 16 on down from 20 factorial, that would leave us with the 20 times 19 times 18 times 17 only. The 16 factorial would be gone, and then we'd have our 4 times 3 times 2 times 1 on the bottom. If you were calculating this by hand, that would probably make this a whole lot easier. 20 divided by 4 would be 5. Here we've got 6, and 18 divided by 6 would be 3. So then you could just do 5 times 19 times 3 times 17, which would be slightly less work. I think most of us are probably just going to type in 20C4 on our calculator. Again, under Math, Probability, and there it is right under the permutation button is the combination button. What do you think would be bigger, 20C4 or 20P4? This is a big number. There's over 4,000 ways for me to choose 4 problems to grade off that worksheet. Let's calculate it. 20P4. Way bigger, right? And why would that be? Well, that's because, let's say I were going to choose problems 3, 5, 10, and 11 off the worksheet. That would only count as one option in those 4,800, where 3, 5, 10, 11, and 3, 5, 11, 10, and 3, 11, 5, 10, and so on, would count for 24 options in this 116,000. So those same 4 problems are going to count 24 times in a permutation situation because we're talking about arrangements of those. So if we're just talking groupings, that number can be expected to be much smaller because we don't care about the order, so we're not counting as many of them. Now, how unlucky would you be if the 4 problems that I chose just happened to be the 4 problems that you didn't do? Super unlucky, right? Like the one set of 4 problems happened to be the one set of 4 problems that I chose. That would be super unlucky. That would be the probability that that would happen. Very, very unlucky. There are 25 members in Math Club, but only 5 can be sent to the state competition. How many possibilities are there? Would this be a permutation or a combination? Do you suppose I care about groupings of 5, or do I care about certain arrangements of 5? In this case, it seems like I'm more choosing a team, like a group of 5. So I would say, since this is a grouping, I'm talking about a combination. I would be taking 25C5. How many combinations, how many groups of 5 could I choose out of 25 total? And that still leaves me with 53,130 possibilities. There are 10 teams in the division. Each team is to play each other team once during the season. How many games are played in the division? So what are we looking at here? Are we We're matching up teams, right? We're pairing teams. We're making groups of 2, right? We're pairing together teams and we're trying to figure out how many different ways we can pair up 2 teams. Wouldn't that work? Does the order matter when we're pairing them up? I would say no. If the Deacons play the Eagles, that's the same thing as the Eagles playing the Deacons. So I'm going to go with order doesn't matter. I've got 10 teams and I want to see how many combos of 2 I can make. I think this will work. And that comes out to 45 groups of 2 out of those 10 teams, which corresponds to 45 games. Probably the most famous type of problem that uses combinations is poker hands. And lots of playing card problems would involve combinations because it doesn't matter what order you receive the cards in most games. So if we were trying to figure out how many 5-card poker hands contain all diamonds, we would have to think, okay, how many diamonds are in the deck and how many different ways would there be to collect a group of 5 diamonds? So since there are 13 diamonds in a deck and the order doesn't matter, I would want to know how many different ways there are for me to collect 5 of those diamonds. 13C5 equals 1,287. So that could be an ace 1, 2, 3, 4, 5. That could be a 2, 3, 4, 5, 6. There'd be almost 1,300 different combinations that were all diamonds. But what if we didn't care if it was diamonds? How many poker hands contain 5 cards of the same suit? What do they call that? A flush? So we could think of that as either diamonds or hearts or spades or clubs. Those are hard to draw. So we know that there's 1,287 of these. And so there would be the same amount of each suit. What does OR mean? Add. So there should be 5,148 ways that you could get 5 cards of the same suit. A lot of times you'll see that calculated in a different way. A very common way of thinking of this is thinking about, okay, so you want 5 cards of the same suit. You need to do 2 things. First, you need to pick your suit, then you need to pick 5 cards from that suit. So how many suits are there? There are 4 suits. And you're going to choose 1. And then, once you've chosen a suit, from those 13 cards, you are going to choose 5 of them. So 14C1, so 4C1 is 4, and 13C5 is 1287, and 4 times 1287 is that 5,148 that we just got. So either way you calculate that, you get that same number. What is the probability of being dealt 4 red cards and 1 black card in a 5-card hand? So this is the first one where it's asking me about probability. So the bottom is just going to be how many different 5 cards hands are there. Remember that there are 52 cards in a deck, and we are going to be dealt 5. The order doesn't matter in this game. And what's the probability that we are dealt 4 red cards and 1 black card? How many red cards are there? Half of the cards, 26 of them are red. Order doesn't matter, and I want to be dealt 4 of those. And then, out of the 26 black cards, I want to be dealt 1 of those. So there's almost 15,000 different ways to get 4 red cards. There's 26 different ways to choose a black card, because there's 26 of them. And how many different hands are there? 2,598,000 960 different hands in poker. Crazy. That comes out to about a 15% chance. Now, 4 red cards and a black card is nothing too special in poker, so that percentage isn't super unlikely or anything. What is the probability of being dealt 3 aces and 2 kings? Now, that would be a special hand. Again, this is a probability question, so our bottom number is going to be the count of how many different 5-card hands we could get. And we want 3 aces and 2 kings. How many aces are there? There are 4 aces, and we want to choose 3 of them. And out of the 4 kings, we want to choose 2 of them. And if there were any more cards, we would have to do another piece of that, but that uses up all 5 of my cards. So that would be the end of my calculation. 4C3 is the same thing as 4C1, actually. It is 4. 4C2 is 6. Pretty small numbers up there, right? Out of this huge number of hands. That's a pretty low probability, which is why that is such a good hand to be dealt. Very lucky hand. 0.000092. Very unlikely to get 3 aces and 2 kings. I remember this always being challenging for me, so I thought it'd be not a bad idea to try a couple more. 4 of a kind, that's a hand where maybe you have 4 sixes and then some other random card in your 5-card hand. What are the chances? So first of all, you would want to choose a kind. How many different kinds are in a deck? Well, there's aces, 2s, 3s, 4s, 5s. There's 13 different kinds in a deck. And first we would narrow it down to a kind. And once we've narrowed it down to, say, the 6s, there are 4 of those, and we would want to choose all 4 of them. Now keep in mind that we would still need to choose 1 more card, right? How many cards are still left in the deck once we have all of the 6s? We'd still have 48 cards left in the deck, and we still have 1 more card that we need in our hand. The bottom number is easy. We always do 52C5. 2 face cards. What are the chances that we get 2 face cards? Well, first of all, how many face cards are in the deck? There are 12 face cards in the deck, those jacks, kings, and queens, and we are going to choose 2 of them. Now, I'm assuming that means exactly 2 face cards, so now we still need 3 cards in our hand that are not face cards. So how many non-face cards are in a deck? I believe that would leave us with 40 non-face cards, and we've already got 2 in our hand, so we would need 3 cards to complete our hand out of 52C5. The more examples you do, the easier this gets, so I hope that helps a little bit.